born and brought up actually in Cuttack. So
I know, he told me that.
Here.
Yeah. So he has good connections there.
Yeah. Hey, what is the problem?
Yeah, I'm ready.
You are ready. Actually, we'll start.
I am ready, but if you want to wait for, I don't know what is the usual practice. If you want to wait for a couple.
No. I'll actually let you know.
Okay.
I think close to 30 fellows have registered, but few have joined only. Anyway, they will be joining possibly.
Yeah, usually these things are difficult to get people.
So anyway, we'll start.
It's up to you. I'm ready.
No. Actually,
up to the organizers, whenever they start. Yeah.
No. The very simple thing. Actually, I will first say actually few words about you, about
Fine.
your, this one, that is the topic.
Okay.
Actually, I will read actually whatever is you have given. That's all. And plus also I will talk about actually this series of lectures that we are conducting.
Okay.
So after that, actually the stage will be open to you, and there will be some questions and answers.
That's fine. Perfect.
Perfect. Format.
Perfect. Yes.
Very good evening to all of you. Those actually who are present in virtual mode to attend this distinguished lecture 71 today. And this series of lecture is being organized jointly by Indian National Academy of Engineering, Bhubaneswar chapter, then IIT Bhubaneswar, NISER Bhubaneswar, IMMT Bhubaneswar, SOA University, then IEEE Bhubaneswar section, plus NISER Bhubaneswar, and also ICT IOC campus in Bhubaneswar. These are some prominent institutions in Bhubaneswar. They are all really join hand to have this series of lecture. And today we are very happy that we have with us Professor P.J. Narayanan from IIIT Hyderabad. His topic is actually going to be interpretability of computer vision. As per his abstract, modern computer vision is based on neural networks that are often black boxes that gives little justification on how they make their decision. This is unsatisfactory for several critical applications. Interpreting or explaining how a network arrives at its decision has been an active area of research in machine learning in recent years. In this talk, he will outline the key concept in interpretability and their uses with respect to computer vision research. Now, so far as Professor P.J. Narayanan is concerned, he requires actually very little introduction, but he is a professor at IIIT Hyderabad and a researcher in the area of 3D vision computational cameras, and parallel computing. He joined IIIT Hyderabad in 2000. He was its Dean of Research from 2006 and was its director from 2013 to 2025, long 12 years. He got his bachelor's degree from my alma mater, IIT Kharagpur, in 83. That is, this is the third, 84, third batch. And was its director from 2013 to, sorry, he got his bachelor's degree from IIT Kharagpur and his PhD from University of Maryland, all in computer science. He was a research faculty member in the Robotics Institute of Carnegie Mellon University from 92 to 96, and a scientist at the Center for Artificial Intelligence and Robotics, Bangalore. He was the president of SEM India from 2009 to 2014 and member of the SEM's Technology Policy Council. PJ Narayan is a fellow of the Indian National Academy of Engineering and an NVIDIA CUDA fellow. With this actually brief introduction, I will now request Professor PJ Narayan to make his presentation. Professor PJ Narayan, please.
Thank you very much, Professor Damodar Acharya, and I really thank Professor Acharya as well as the INAE Bhubaneswar chapter and all the other institutions who are organizing this for inviting me. It's always a pleasure to be part of this. I was involved with INAE, the sectional committee, also a couple of years ago. Yes. So I think we need to have more activity at the INAE level so that the engineers come together. And today is the time of multidisciplinarity, which means you should all think of ourselves as engineers, not just computer scientists or mechanical engineers, etc., because this is the time where things have to work together. So I have been working in computer vision area since my PhD days, 35 years. So and AI has been, computer vision is part of AI now, and AI has been progressing very quickly in the last few years. So why I chose this topic is it's a very important part of AI, which is not often recognized enough. It's also a new area, relatively new area, because when AI becomes very active, that's when these kind of questions come. So my presentation will be a very brief, very broad one, not necessarily with too much details on any of this techniques, but I will also start with the why this kind of problem has become important in AI. So I'll share my slides now, and I hope you can see this.
Oh, sure.
Yeah. So interpretability, we'll come to what interpretability is. Before that, I just want to say where we have progressed in terms of computing. The use of computers is now everywhere, from your mobile phone to your desktop, laptop, your watches, all have computers, and they do sophisticated computing. And computer science or computer engineering has been working with building better computers and ensuring they work well. So I like to say there are originally two primary concerns of use of computers or computing, which includes hardware, software, building, etc. There were two concerns. One is called efficiency and performance. That means if you are, is your computer working well? Is your program working well? Is it, how fast is it? How much resources take? Hardware, software, networking, bandwidth, all the building better and better computers. That has been one of the major ideas. But in the computer science side of it is about making sure what we do with these computers is the right thing. Can we guarantee that what the computer is computing is correct? Can you guarantee it'll do these things in a fixed amount of time? A lot of theoretical concerns about these, and these have been the primary concerns. In the last few years, once the computers have become very powerful and have been processing all kinds of data, not just, earlier computers were processing all kind of engineering data to design better aircrafts or design a rocket and very, very serious tasks. Whereas today computers are used for everything from gaming to making documents to, everything is done on computer. So when the good computers are there and good programs are there and they have a lot of data, a new concern has come into the computing paradigm, which is I like to call intelligence. When you do things again and again and again, can we learn from that process? Can we learn from the data? Can we learn from what we experienced earlier? Okay, this is what we call intelligence. And these three concerns are not independent of each other. They are intertwined. Intelligence, efficiency, and guarantee. This intelligence, you can think of recently the importance of intelligence has exploded, and that's typically called AI today. So in AI itself, in the AI world, how it differs from the traditional world. In a traditional computer application you have a processor, and into the processor you load your code. This code may be for a work processor, maybe controlling a electrical machine, maybe something to play a video. That code is loading on the processor. Then you give input to the code, and you'll get output. This has been the way of using computers for all these years. Okay, and where do you get the code? Human programmers sit and understand the specifications and the domain knowledge. That means if you are doing a rocket control, what is required of rocket control? What are the equations governing them? What are the inputs required? So you understand the problem, understand the specification, use some language, C language, Java language, and they create this code and test it and all that. That code goes here to the processor, and then with the code and the processor may be your Intel microprocessor or some other machine. Together, this code plus input gives you the output. The focus in this is being to create the code or the program. The processor is pretty standard. The Intel architecture has been around for 30, 40 years. It's been dominating all these years. That's a standard model. Code is created by humans mostly. There have been attempts to create automatic code from specification, not been very successful. Okay, and the standard models like C, C++, etc. In the AI era, this has changed slightly. What we now have is an ML model or ML system. And that system may be called a neural network, may be called a support vector machine, it may be called a Bayes classifier. They are defined by the parameters. The model is like the processor, the parameters like the program. And again, this may be input, maybe images coming in, output is you telling me who is in the image or what is happening to the, if you give an audio, what is the word you hear, etc. Now, these parameters, how do you get these parameters? Parameters are obtained by this process called the training of the machine learning model. And training takes input-output pairs. You give lots of examples, correct examples, wrong examples. That is, if you want to recognize faces, you give lot of images of faces of the right person and the wrong person and give the corresponding answers. From a large number of question and answer pairs, the training algorithm will find the parameters for the model, will fit the parameters such that the outputs for all the inputs will be as close to the real ones as possible. And then these parameters are loaded into this ML model, and this works as your trained face recognition system or trained speech recognition system. And whenever new images or speech is given, it gives the corresponding output. So this is it looks same, but here the program is really not written by humans. It's automatically created from input-output pairs using training. So your focus is on the model and parameters and not processor plus code. If you can fix an ML model, such as this kind of neural network or this kind of transformer, then parameters do all the work. Okay, training system creates the parameters. This has been the model that behind all the AI systems, but this has been around only for like 10, 20 years, so it's still evolving. Just like old days when there were all kinds of microprocessors, all kinds of processors. Later, it turned out it's convenient to have one or two processors only, so Intel became that standard. Similarly, similar thing may happen some other time in machine learning. Still early days, you create special models or special architectures for the machine learning system for each application. That's the place we are right now. Now, what is an ML system? Once a trained ML system, typically these are called models these days. You say it's a model, trained model. I like to call it a system. An ML system has two parts. One is the input, whether it's an image containing faces or some audio signal containing some speech or a spreadsheet containing some data. You have to represent it you have to represent it in a way that the machine learning core model can understand. So for that, from you extract the relevant information, typically called features. These features are taken from the input data, image or sound, etc. And once the feature is extracted, you throw away the original image. You just deal with the features because the features are in some way you designed yourself. Okay, and features are typically vectors in high dimensional space, maybe 1,000 dimensions, maybe 10 dimensions. In image processing context, a feature can be thought of as important points in the image, and edges in the image, the lines you see, or some corners. There are features like SIFT, which measures the local gradients of intensity, the frequency domain, what are the frequency domain components in the image or speech, etc. These could be the relevant information with which you represent the input signal. After representation, you have to, so this is, you call it extract feature. The input, you extract the features of the representation. Typically, this is done manually, or all this used to be done manually, and now the input data is represented using feature vectors. After that, you do the classification. That is in a task where you're trying to identify people. Classification, or some in general can be called inference. You take the feature vectors, and for each vector, you have to give the correct answer. This is the trained machine learning model. Give an answer for each representation of sample or representation of each sample. And the machine learning model is a function fitting that approximates this feature vector to answer function that maps feature vectors to answer using, like I saw earlier, what we saw earlier, using a training procedure. And the training can be for a linear model, linear classifier, a support vector machine, neural networks, random forests, k-means, etc. These are all fit in this box. Okay, they all take the appropriate feature vector and give the answer. So this is the anatomy of a simple any machine learning system. Now, as AI has progressed, AI or machine learning has progressed. In the early days, AI was based on trying to approximate human knowledge, how to extract how experts do. So the earliest AI system was a diagnosis system that takes some symptoms and gives, this is the disease you may have. Just like a doctor will ask you, do you have fever, do you have some pressure, what do you measure your pulse, measure your some other parameters, and then based on the thing, you give an answer. So how do the programs or the computers are very simple. You could write this if then else program, expert systems, rule-based system. So these were the early AI systems where everything was the representation, the features were hand-tuned. You want to decide the disease will be diagnosed using temperature, pressure, and some blood tests. That's the representation. And reasoning is the logic encoded in the program. Okay. Then this was not scaling much because you cannot just go to experts and get all the information out enough to create practical system. Then there came the era of statistical machine learning, or just machine learning era. Now the models became somewhat standard model, not a program that consists of if then else. For one disease will be different from another disease, etc. Here the model is maybe the hidden Markov model, or probabilistic Gaussian model, or support vector machine, random forest. These models were fixed, okay, and the representation was still by the human beings. You say these are the relevant parameters, the feature contains these, but the mapping of the features to the output is done by a model which is trained using statistical method, or this training process, which is really fitting a statistical function. Okay, this is the second generation of AI. Third generation or current generation of AI went one step further and went to deep learning, where there is a large network. The machine learning, core machine learning system in a statistical or machine learning method also could have been a network. But here there's a large network, typically a convolutional neural network or a recurrent neural network and multiple kind of networks. The difference is the representation. The input to this network that you give is the original image itself or original sound signal itself. You don't extract features explicitly. You let the system figure out what features work, what features don't work. Okay, that's a critical difference. And when that happens is, if you look at a DNN system, a deep learning, deep neural network system today, it has multiple types of network nodes. Okay, so there is this famous network called AlexNet. This came out in 2012. This is the one that first showed that these large neural network can solve computer vision or recognition tasks in computer vision very, very effectively. This had, you can see several layers. There's the input, there's some convolutional layer, there's a pooling layer, another convolutional layer, another pooling layer, and they are this fully connected layer. And finally, there's a softmax layer, and this gives the output. This is the 2012. Many systems were built later. Another VGGNet, which is a very popular one. It has a structure like this. There are different ResNet, all kinds of networks. Later today, there are transformers, which are also some kind of networks. So if you look at this, say the VGGNet as a machine learning system that I outlined before, the initial, you can think of the initial, all these layers for up to this pooling layer here has to be extracting the right features, relevant features for that problem. Okay. And the last three layers here, or four layers, which are fully connected layers, they are like the traditional machine learning model or a neural network model that was used in 70s and 80s also. So the classification done by the last few layers, the feature extraction done by the first few layers. So you are giving input as input the original image itself or the original audio signal itself, original text itself. Finding the relevant parts that matter for this problem is the job of these layers. And during training, it'll do that. Okay, so this is how a modern neural network-based, deep learning-based system can be thought of as extracting features in the first and then classifying it using the last few layers. This is a general approximation. Okay. Now what happens is these systems tend to be black box. You don't know why is taking a particular decision. Okay, they achieve fantastic performance, but their internal decision-making process is opaque. It's not instructive. You cannot look at it and say why is it making this decision. First of all, these are very high because it's very, very complex. Millions of parameters, billions of parameters are there in some of the networks today. And these networks, the model is simple, architecture is simple, but why is it doing what it's doing? And why is this one image I give, it gives an answer as yes, another image I give, it answer as no. Why is this happening? So this is okay if your application is not very critical, but if a critical application, maybe medical diagnosis, maybe you are controlling driving a car, the self-driving cars core AI system. Here we need to know that the system is making decision based on the right factors. If the AI system is giving you, say, one of the AI systems that probably all of you use regularly is what is called recommendation system. You listen to a few music, and then the system will tell you maybe you will like this other music because other people who listen to this kind of music has chosen the other kind of music. So in such places, if you don't know why it gave this recommendation, it doesn't matter because application is it's a lightweight application, not very critical application. But that's not true for real life application, many of the real life applications. So that's where interpretability comes in. How do we understand the decision made by such a network? What property of the inputs contribute to the decision? If you ask, you show an image of a person or an image in which one person is standing to any human being and say, is there a human being there? They said, yes. Why do you say that? They'll say, look at this region. I see a head, I see eyes, whatever. I see someone. That kind of explanation or something like that can these networks give to make us confident of whatever decision is making. Okay. So it's not enough to have just good performance. We need to know why and how the decision is made in most cases or many cases, a medical application. If you are making a decision on admission, Now you have your AI system go through all the application and say you want to select this person or not. Now you don't want to just do it randomly and some system is doing something in a black. You need to know it's doing the right factors it's using. Okay. So how do we understand the decision? That is the core of interpretability. Now there are two terms in AI today, popular term, interpretability and explainability. As you can imagine, interpretability is able to interpret why each decision was made. Explainability is about explaining how this thing works. So explainability turns out to be a broader concept. How can we explain the results based on the inputs? There are some people who say explainability is about why some decision is made, but interpretability is about how it was made. But in practice today, these two terms are used very interchangeably, and there is an area typically it's called XAI for explainable AI. That's a broad area under which all these things stand. And this is a relatively new area, and a lot of work is happening now, but not a huge lot has happened because these systems have to be serious and to be put to good application. Only then these concerns of explainability came to the minds of the people using it. So the XAI methods there are broadly you can classify into two, where global methods where the explained model is the model behavior explained in the entire data set, which feature is important, etc. Local is about why this decision was made for this particular image, that kind of thing. Now another way of looking at this XAI method is model agnostic. That is a method that will work on any ML model, any neural network model, or model specific, something that is tuned for a particular network. That network will do very well, but other networks it cannot, you'll have to tune it again. This is the broad classification. If you look at some of the techniques that exist there, XAI technique, firstly, there are three major types. The one is post hoc explanation. That means you have made the decision and you want to know why the decision was made. So you look at and say this decision was made because this is the reason. You're just explaining it. The other one is you create the model in such a way that it's inherently interpretable. It takes some of the relevant factors into the design of the network. Third one is typically the very new one called what they call mechanistic interpretability, looking at what each component is doing. Okay, that's a very new area. In post hoc tools itself, the two things that we saw earlier, something that is model agnostic, that is can work on any kind of model, or model specific, what is designed for each model. There are methods like GradCam, LIME, and SHAP. These are all things that came out in the last 5 years. Under the model agnostic category, the model specific category, there is concepts activation vectors, concept activation regions, and other things. In the inherently interpretable model, this also came out in the last 3-4 years. Concepts bottleneck model, where you first design concepts and then design the classification. In mechanistic interpretability, there are circuits, there are sparse autoencoders, and a few methods. What I'm going to do is to look at some of these very quickly, give you what they do. It's not possible to explain how and what these things work, but just to give you what they do and why is it a step towards understanding the network's decision making better. Okay. So this field, I mean, this is a timeline. If you want to say the deep learning became very serious. I mean, it's not right to say it is the start of deep learning, but deep learning became a serious paradigm with AlexNet. After that, there was no looking back. And so in this LIME kind of method started coming in like 2016, etc. The concept vector method came in 2018. GradCam came in 2017, and some of the mechanistic methods came recently, and so on. Okay, it's just to give you a sense of that these are not a very old area. And so some of the model agnostic post hoc models. Post hoc means after training everything is done. You take one. If you give one decision, one sample or some model, how is it performing? You are not changing anything of the model, you are just examining it. Okay. So this LIME is one of the methods that came early. Here the idea is to explain an individual sample. I give this particular image and gave it to the recognizer. It says there is a dog there, there's a guitar there in that image, the classifier, the machine learning model. Now you want to know why did it say that? Why this model said that? So what it does is it takes that model, perturbs that image, that sample, like this model shown in the image shown here. You perturb its the component slightly. That is some part, the pixels actually, some regions of the pixel will perturb or change slightly or greatly, and then see how the classification is affected. By looking at that, you can say the cat. If you say, if you want to explain electric guitar, it says electric guitar. It shows because of these components. Looks like this is the one that makes it electric guitar. Acoustic guitar, it's because of this makes it acoustic guitar. A dog or a Labrador, because this is the one that making Labrador. So this is all learned by perturbing the image locally and looking at how the classifier behaves on these perturbed images and studying that process. But you can see this quite useful. You can ask the question, if you said there's a Labrador dog in this image, why did you say that? He'll do the analysis and give you that these things. He said, this is the reason. And this gives you some idea that looking at the right pixels or right region of the image to infer or to decide that there is a Labrador dog there, and so on. So this is one method. Another method is visualizing how this thing is working, how a CNN is working. This is called GradCam. It came in 2018. The goal is to, again, tell which parts of the image contributed to the decision. Okay, and with the CNN overly overly relied on some parts of the image or some part of the data to make this decision. So, for in this image, this image, your classifier said there is a dog and a cat there. Then you ask, why did you say there is a cat? Then it shows this kind of image called a heat map. It says the red indicates maximum, or these colors indicate maximum contribution. It says these are the pixels that contributed maximum to the decision of cat or the class cat. And dogs, these are the things that contributed more. So what happens here is these neural networks are trained using what is called back propagation. You go from the output is not matching, the error you propagate, the gradient of the errors you propagate back. Okay, so this GradCam propagates the gradient back up to the last layer, or the final convolution layer where feature detection ends, and then finds out the maximum the activity there and maps it back to the image. So it says maximum activity is happening here to decide on there's a cat in the image, and maximum activity is happening here to decide that there's a dog in the image. Here is another example using a different network called ResNet. Cat is this region and dog is this region. Again, you can see that we can at least have a comfort that the CNN is looking at the right parts of the image to make the decision. At least it matches with your our intuition. Yet another method we don't want to say a lot about is SHAP. Here, the idea is to say you have a feature vector, 10 features or 100 features were there for the feature vector. Which features contributed more to the decision? Okay, so here is a you want to say somebody to be declared as a home, to be a old home, working class home, new home, etc. That's the problem. And there are multiple features, number of rooms in your home, there's some concentration of something, the distance, remoteness, the crime rate in the area, tax rate in that area, pupil student ratio, all kinds of features. And what this shows is, in particular, decision making, what contributed more. You say number of rooms was really a factor very strongly for this particular class, whereas some other class it may be something else. Okay, so the idea again is, I don't want to give into details, but the idea is, if you are using 10 features, which features were more prominent for a particular class of decision? If you say if you found a dog, which features were prominent there? So this kind of thing. Again, it's an idea of looking at what contributes to the decision. Okay. Now we go to some model-specific tool, which is not for all models. Earlier, these three methods just look at how a model works. Now here it is specifically for each model. So there is an idea of a concept. Okay, concept, as we understand concept is an abstract, human understandable representation or component of the data. Okay, for instance, in an image, the color colors may be a concept because you depend on colors to make some decision. The texture or the variation of intensities in some regions of the image may be something that you look for to decide on if there is a grass there or something else there. Similarly, some stripedness or some circular shapes, these kind of things are called concept. This, of course, humans understand it. So the idea is to look for the importance of these concepts in decision making. Okay, in the trained network. If there are sometimes what happens is a network learns from the wrong concept. If all the network does is you give a lot of inputs of cat images, it gives you cat as output. You give a lot of images of cow images, it will give cow as output. But is it looking for the right concepts to say this is a cow there or a cat there? Or is there some bias of some kind? So we'll look at it now. This is a search I did on images of cow. Okay. If you search it in Google, you search images of cow, I got all these kind of images, many more images. And now I can use these images to train a classifier. Okay. And there are cows in all the images, and you say these images contain cows. Then I take hundreds of other images which has no cows and say those are the images with no cows. So the positive examples are these kind of images, negative examples, other kind of images. You train a ResNet or VGG, some network to detect cow. Now you start giving new images of cow, should say yes or no. Okay. Now, if you look at, anybody looks at this picture, one thing that you will notice or you can notice is that, yes, all of them contain cows. We can recognize the cows, but all of them also contain a lot of grass or greenery at the bottom of the image. Okay. In fact, the pixels that contain greenery at the bottom of the image probably more than the cow pixel. So a trained classifier doesn't know what to look for. Maybe just learning, looking for green pixels, grass at the bottom of the image, and if you give an image of with green grass and some lion or a giraffe standing on it, you'll still say it's cow because it was influenced very greatly by the green color at the bottom. This is very much possible. It picking onto the right thing. We don't know. This is exactly the explainability problem or interpretability problem. So is the system influenced by the green color at the bottom? Is it biased towards color or is it actually looking at some properties of cow? We will hope that it's looking for some properties of cow. Okay. So here is where concepts come and concept applied as concept activation vector. If you look here, this is a concept for stripes. So if you're looking for gorilla, zebra, for instance, you know, zebras, one of the characteristic feature is the striped shape. You can see here. So a concept could be striped versus non-striped. So you take a lot of images where there are stripes on the right side, on the left side, you see a lot of stripes are there. On the other, and you also take images where there are no stripes, and you pass it through your network, your classifier network, and look at where it, where the images with stripes go and where images without stripes go in this layer, one of the layers, and see if there is a easy separation. They look at a linear classifier that separates the striped images and non-striped images, or in one side and the other side. If that is the case, now you know that somehow here stripe is a major component. Okay, so this is what. So you take the concepts, you find a separating linear classifier for the positive images of the concept and the negative images of the concept, and this direction, the separation direction here, vector says if a new sample has a lot of component in this direction, it may be because the stripiness or because of color, whatever concept you use. So TCAV is a score that you can use, which based on the directional derivative. Another we will see this in a little more detail later today in my presentation because I use it for something else. But at this point, you know that you're trying to look at concepts like color or texture or stripedness or roundness, and you create a lot of examples with that property and without that property, and send those examples through the network that you are using for classification or for your AI task, and look if at the output layer, they are separated well. If they're separated well, that means there is some possibility that this particular concept is playing a major role in the classification. And if that's not what you want, you should do something. And that's what we'll see later. This whole thing has been also extended to what is called concept activation region. In vectors, you just take one linear boundary and a vector towards that. Here you generalize to a region of this activation space or some high dimensional space where this concept lies. The concept may not lie nicely in a straight line. It may lie in a more complicated region. So you're extending it to that. This came in 2022. And so those are about the model, those require the model. Now we look at quickly what does inherently interpretable architectures mean. Very simple, we'll say there is a thing called concept bottleneck models and concept embedding model. In the concept bottleneck model, what happens is, again, the same concept that we discussed earlier. Suppose you want to look at birds, you want to classify birds. You know the important aspects of birds is their color, their beak size, their head color, their some of these property. So you, instead of directly giving image of the bird and telling its type, the bird, which bird it is as the output, you first learn the concepts of beak length, total length, color, underside color, these kind of things you learn first, and then using that you classify. Here you know you are forcing the system to look for these particular properties that you know, human with human understanding, you know are relevant for this problem. Similarly, if you are designing a medical imaging, an X-ray classification system, the doctors can say you look for lumpiness somewhere or some breakage somewhere, etc. So you first design networks to learn that concept and use those concepts in the final classification. So this way you are by design you are incorporating explainability, interpretability into the system. So these are reasonably popular, not very popular, not too popular. And the last line which we'll very quickly look at is what is called mechanistic interpretability, where the idea is to look at, these neural networks contain neurons. What is each neuron doing? Okay, you look at the activations of different parts of this network and see what is each neuron doing. So you would see there are mechanism by which you can say this particular region is looking for colors, this particular region is looking for, say, some texture, this particular region is looking at round shapes. So this kind of reasoning can be done. There are some tools to do that. They're reasonably new, very new, 2023, 24, they started coming. I will not say too much about it. All I say is that all I want you to know is such things exist, okay? And now I would like to talk a little bit about how interpretability can be turned into action. By action, I mean by improving this classifier or whatever neural network model. This is some work we did a couple of years ago. So the basis is, if you look at a neural network, okay, it's an input, there's level 1, layer 2, layer 3, layer K, and final softmax output. Okay, input vector, this may be the whole image or the audio signal or some language vector. This goes through transformation. After first layer is processed by the first layer, there's some other vector representation, then some other vector representation, some other vector representation, etc. Okay, so at each, so if you have 4 classes, think of a classification problem with 4 classes. There are triangles, diamond, circle, and star. So initially, inputs are just images, say, they are images, let's say, images all mixed up. Even the first layer, all of them are mixed up. They are not separated. Second layer, probably they get started separating a little bit. Third layer, it's separated a little bit more. In the last layer, hopefully each of those are separated into different parts of that activation space, that vector space. And now you can classify easily by just looking at this region belongs to star, this region belongs to diamond, and so on. This is what happens in any neural network. As the input vectors go through different layers, it's getting transformed into different space, and hopefully, because it's trained to recognize such a thing, the last layer contains enough information to separate class A from class B from class C, etc. Okay, so this is what happens. Now, what we can do is what happens at intermediate layers to to each of the class. You have 4 classes. These 4 classes are represented by particular some names in the last layer, which we know. The 4 classes may be like gave their star, circle, diamond, etc. But at the middle layer, layer 3, layer 4, where does star lie? Where does circle lie, etc. These are called prototypes. So if you take all you have labeled data, by the way, you have a lot of images or examples where it says these are all diamonds. So all these diamonds you send from the start to the left to right, and in the particular layer I, all the diamond images lie here, okay? And they can be represented by their mean, let's say, or a few mean vectors. And the triangles go somewhere else, and this is their prototype. The circles go somewhere else, they are their prototype. And the stars go somewhere, and this is their prototype. Remember this is not neatly separated at this layer, but since we have labeled data, we know which one go to the rectangle, the diamond, which one go to triangle, etc. So we can do this. And these prototypes play a role in trying to understand what's happening there. So what I'm going to present very quickly is this paper that we wrote 2 years ago with 2 students of mine. It appeared in NeurIPS exactly 2 years ago. So here again, human-centered explanation for model improvement. This explanation or interpretability is now used for improvement. So again, this is back to concepts, as we discussed earlier. Concepts like texture or color, etc., are abstract human understandable representation. You can identify concepts by giving these positive and negative examples, and learn activation vectors, as we saw earlier. Okay. And the concepts are typically defined or identified by concept sets. If you want to say a texture concept, you have to give lots of images with texture and lots of images without texture. Okay. Similarly, if you want to do round shape, you have to give a lot of images with round shape and many images with no round shape. And then the system will be able to, the concept of roundedness can be learned by looking at the difference between round shape images or round shaped examples and not the other ones. Okay. So now here is what happens for say texture. This is a look at concept set. These are the texture concept positive examples. These are the negative examples. And you are sending it through your trained network. Okay. And some layer I you choose. In that layer, all the texture ones come here and the non-texture ones come here. Now there is a nice line separating them, and this is the normal to that line or normal to that plane, that linear that separates them, if you fit a linear classifier. Okay. So this vector is called CAV, concept activation vector. Okay. And how is this used? If you look at sensitivity, okay, you take one example, and this is the concept direction, and all networks work on gradients of the loss function. If the gradient of the loss function is grad LO at this layer, and that is in this direction, the gradient is this direction, you take a dot product of that with your concept vector. And if the dot product of this concept vector with the gradient vector is positive, that indicates that this particular concept is influencing the decision. If it's zero, that means the gradient and the concept vectors are orthogonal. Means this concept is largely independent of this. This system is largely dependent on this concept. Okay, this is what called sensitivity, and this has been reported by different people to study. So this can be used to study. After you design your cow classifier, you give a green color concept and give it to the classifier. You may see that the gradients are very strongly aligned with the green color, which means that the classifier was very heavily biased or influenced by the green color at the bottom of the image. Okay, this is the typical example. What we did is, if you know that a particular concept like texture or color is playing an important role, and you don't want it to be, in this example, the example that we will be taking, we don't want green color at the bottom to be playing a role in classifying a cow, because that's not relevant. One way you can do is to create millions of cow images where cows are there with green grass, no grass, blue sky, no sky, red sky, all kinds of situations you can train, then it probably automatically learns. but it is natural that cow images will have some green grass, which means that bias is kind of natural. So if you have that, you know that from by looking at the sensitivity, that is the dot product of the gradient with this concept activation vector direction, you know that there is some influence. In neural network training, you can fine tune, you can slightly fine tune this network to make this dependence low. How do you reduce the dependence? You can maximize or minimize this dependence by introducing a additional loss. This loss called concept loss. This concept loss is directly, you can see it's just the dot product or cosine of this gradient with the concept activation vector. And you know that if that component is strong, the dot product or the projection is high, whether it's negative or positive, then it is going to affect the decision. If you don't want to affect the decision, what you do is you add an LC, an additional loss to the original loss term, and fine tune, retrain the algorithm a little bit more. Okay, so you find this concept loss and add to your original loss. This L0 was the original loss with which your network was trained. To which you add a small LC, the concept loss, with a small lambda to minimize or control it the strength. Okay, and this is the final loss. You run a few rounds of what is called fine tuning rounds. Now what happens is the weights will change here to make it less and less sensitive to that particular concept. Okay, and this is the basic idea. And here are some of the examples on which we showed. This is called an MNIST dataset. MNIST dataset is handwritten characters 0 to 1, 2, 3, up to 9. And these appear, if you have, there are a special color MNIST dataset is where all zeros are written in, all the zeros that appear in dataset is written in red, all the ones may be written in green, all the 7 may be written in blue, and so on. Now you train this a neural network to recognize 0, 1, 2, 3, up to 9. Maybe it's just picking up the color. All red will be told 0. So how do you make it free from the color, bias from the color? Similarly, you have created data sets where texture is added. Some patterns were added to each of these images, and then see how it performs. Decoy-ness is some variation. The image is varied. You see some extra things are added. There are other data sets where this is a data set where your BFFHQ is predicting the age of people. Okay, looking at an image and you want to say what is the guess, young or old or something. But it so happened that if you give all young as women as, young picture for women and older people are all men, then it's probably learning that rather than the age. So this is another concept that you can try to understand if the network is learning that, and then work against it in the way by introducing a concept loss appropriate for that, as I explained earlier. So here are the results for the color MNIST and texture MNIST, etc. All the other methods had these are the accuracy values. Ours was improved by improved a lot. From these 20s and etc. we became 50s and 90s. So we are this method improved, and this is data set which has this bias problem. So we have overcome that by this method. In that BFFHQ, the age bias is there. So your the old systems were giving, the basic system were giving 50s and 60s. We could improve it to by just looking at training for a age concept with a lot of young people versus old people images you take and find the concepts same way that we explained earlier, and then introduce a loss that works against it. So these are the kind of things. Here what we have done is you took an interpretability tool, which is concept activation vector, and used it to improve the model by defining what we call a concept loss from it. And then you have to now fine tune. This is now not just interpretability. Interpretability turned into a little bit of action. Okay. So we have a couple more works along this direction, but I just wanted to present something that is easy enough for a general public to business population to understand. So in conclusion, deep neural networks are at the core of every machine learning AI system today. You say transformers are the basis of all these LLM. The transformers are nothing but some specific kind of deep neural network. So it's essentially those deep neural networks, convolutional and other deep neural networks. And training them using input-output pairs is how any AI system is built. You know about these LLMs, they're trained with billions or trillions of data items, and it costs a lot of money to train them because it takes a lot of compute effort for that, to train them. Okay. But again, it's all input, output, some training. Okay. And these models tend to be opaque, black boxes. You don't know why it is saying, it's taking some decision or it's giving out some value. And interpretability or explainability is the broad idea of bringing some understanding to how and why they are taking whatever decision they are taking. Okay, and this is very, very critical for using such systems for important application, medical diagnosis or decision making that you do. Say self-driving cars, if the camera or information is, it says stop now here or turn left or turn right because I see some obstacle in front. You have to be sure that the system is looking at the obstacle and making a decision, not because there was some paper flying on the corner of the camera and it somehow got confused by that. So you have to be very sure because the system will be running on the roads, right? So there are many applications where we need to understand. So the interpretability and explainability tools are there to at least open the black box a little bit and get some comfort on why and how these decisions are being made. Several methods have been devised for this. We saw a quick run through some of them. Interpretability can also be used to improve the system, like I showed in the last part. This area is in very early stages right now. There is a lot more to be done in the future, and there's a lot of work happening in machine learning. Actually, this interpretability, explainability is one of the very hot areas, along with, of course, all the LLM training stuff, etc. That will always be there. So it's people are looking for new problems to solve or research problem. This is interpretability. It's not an easy area to get in. You have to understand machine learning, understand many other concepts, but it'll have a long future for it. So I'll stop now. Thank you. Thanks to INAE Bhubaneswar chapter, Professor Acharya and others for giving me the opportunity. I'll be glad to take a few questions if there are any.
Sir, you're muted, sir.
Who is asking the question?
Sir, actually, Damodar sir is muted. That's what I'm.
Okay, Professor Acharya, yeah, you're muted now. Okay.
Okay, when he comes, can I ask a question? Am I audible?
Yeah, sure.
Yes, sir.
Go
Yes,
ahead.
sir.
Okay, I'm a total layman. Total layman means total layman. So I'm going to ask you probably very simply, you may be able to answer. I got problems with the Aadhaar system fundamentally. Okay, I will put the problem like this. My fingerprints are all okay. I'm not all that old to my fingerprints have gone. And when I take my life certificate or the Jeevan Sati, vagara, I carefully make sure that my finger is clean, etc. And I have bought the correct fingerprint reader. Now I connect it to Aadhaar system and that it says reject. Then it gives the automatic, no, the thumb dalo. Then if thumb is not there, okay, first finger, second finger, something it will. Now, 2 days later, I go to an immigration office, particularly US immigration office. Those fellows also want fingerprint and they are accepting. So that means there is some difference between the Aadhaar algorithm that is used in image processing, my fingerprint, and what the Americans are using. Can you elaborate on this? What is exact? How does the system recognize between the ridges and valleys, first of all? I don't know whether you will say some shading again. I don't know what it is. First of all, we start with that. It is supposed to recognize the ridges and valleys and the patterns of the ridges and valleys. How does it do it? This is question 1. Question 2 itself I will now ask then later on. Can we, police use this image processing very much, quite a lot. Now, can they, by any mistake, can they catch hold of a wrong fellow and then say, now you are the thief because my AI is telling that you are the fellow here. Is it possible? These are 2 questions.
Okay. So regarding the first question, I mean, I'm not an expert in fingerprint or biometrics, but today's biometric systems actually are not using the ridges and all those thin curls and all right now because they are, today's system just takes this image as a whole, okay, and the deep learning system. But yes, the algorithms used by Aadhaar are the very best in the world because Aadhaar is simply the most complicated and most sophisticated biometric system in the world. With 1.5 billion people, we have that might, okay? And their algorithms are supplied by unfortunately, their algorithms are supplied by global, which mean non-Indian companies. That's the problem. In fact, one of my colleagues here is working with Aadhaar to develop an indigenous matching and other algorithm. That's a problem. So that lot of factors depend on this. The particular device you use is obviously very important. Okay, the device, if the device is and the device that you used while you are registered. Typically, those devices are used by, I mean, there may be the
10 years ago. Oh.
Old one or the inexpensive one, they may not be used properly. So if your recording was done incorrectly or badly, then it's very difficult later, right? So these are the parameters. Maybe the American immigration system uses, you registered probably more recently also. That is also possible. Typically, the changes happen, and if you register today, the probability of you being recognized correctly or incorrectly in the next few years will be higher because slowly changes. So maybe that's also a factor. I'm just guessing. Now, regarding your second question, that is the big problem in AI systems, is that you could easily they make mistakes. All of them make mistakes. They make mistakes, and when they make mistakes, it is depending on what use it is for. The mistakes are very, very serious. The example that you gave.
Computer has told me, therefore you are the fellow.
Yeah, that's true. But the real problem is that it's used for a very critical application. Somebody goes to jail or not is very, very big decision. That's why I said, if your AI algorithm is used to show you the next song to play or next image, next website you go, that's okay. You make a mistake, nothing happens. But if the AI algorithm is used to drive cars, that is serious. And the AI algorithm is used to take people. So there was a famous example of some company in the US. They said by using images, this data, hundreds of data, we will tell you if somebody, a convict, somebody who's was in the jail, was released from the jail, is this person likely to create a crime again? Some they will predict by using some image or voice. I don't know what all they use, a few things. Now, obviously, this is so critical. There was so, and obviously it make mistakes. Maybe it's right 99.9% of the time, but then, what does it mean? Yeah. Then I think they have to remove all these things. They have to applying. So this is exactly the danger today of applying this AI to very life critical situation, including such situation. You have to be very careful. So interpretability, explainability is a small step towards understanding that this is, you are making the right decision. But in a real system, we are still very, very far from that. Okay, so AI systems should only be used to help human experts. Okay, and you say, I am saying there is a tumor here because I see this region of X-ray or MRI image, I see suspect. And the doctor should look at it, doctor should remove the AI and say, okay. So doctor is unlikely to miss this decision. Okay. Now, same thing in a judicial system or a police is very difficult to even for me to define what is it, but the spirit should be they will help, they will give, they say that this person is likely to, this person may be the person who committed the crime because the height and weight or the color or this way of walking seem to match from the video that you captured and what you getting. But you should take the decision yourself based on more factors. This is the right way of using AI. Otherwise, you are in trouble. We'll all be in trouble.
Thank you, sir. Thank you. Very good. Thank you.
Any other question?
People ask questions.
No. There are
Go
many
ahead.
people present here. So, Professor Renu Sharma, would you like to ask some question?
Sir, it's not the question, sir. It's just a representation. Like our computer science department, they have taken up a project and they use these techniques for identifying the health of cows by the various movements of their body. Like if they are happy, they will nod their head, move their tails, and these images and these data are captured, and the network is trained, and accordingly, the production from the dairy will be good or bad is decided, sir. So your lucid presentation really enlightened much on this aspect, what I learned, and it is very useful for our the people, those who are doing this research work, sir.
You're part of SOI University?
Yes, sir. I am Dr. Renu Sharma, Additional Dean, Student Affairs,
Yeah.
and
I only see your name. I don't see where you are, your affiliation in the.
No, she is actually pillar to our all activities here.
Oh, good. Thank you for creating that. Yes.
Now, anybody else actually who would like to ask any question? Now, of course, actually, can actually this AI be used for the medical diagnosis?
No, they are being used. The positive point is every country in the world is lacking enough well-trained medical professionals. Okay,
Yes.
the number of doctors per population, and then you said doctors. You need so many radiologists. You need so many skin specialists. I mean, if you look at that, the gap in any country, especially poorer countries, India and all, is very, very high. Okay, so can we? I mean, this is a technology that can reduce the impact of the gap, but again, it has to be used wisely. So if instead of, so there are many screening efforts. So we designed in IIIT, we built a what is called an oral cancer screening app. You take your mobile phone camera and take an image of your mouth cavity and send the image, and what it's going to say is not going to say you are risky. You're going to say it'll say no, you are risky at all or you are not at all risky. And if the system determines there is some risk level, it asks you to go and consult a physical doctor, an expert.
Yeah.
Not that it says you have something to take medicines at all, because very sensitive, right? You don't want to scare people. You don't want to miss people either. So that's the other problem when you make a decision, and the decision is you don't have to care, you don't have to worry. You seem to be okay, and then few weeks later that person gets into difficult situation. What happened? That risk is there, but in screening, the idea is exactly that you be a help and you tell the individuals you better consult a doctor. Okay, and this kind of screening applications are plenty. There are many applications of especially the radiology, that is looking at X-ray, MRI, CT scans.
Yes,
In
yes.
fact, so much so that there's a joke in 2016, I think 2016, 2017, one of the major AI experts called Geoffrey Hinton, who got the Turing Award as well as the Nobel Prize for creating this. Jeffrey Hinton famously said in 2016 or 2017 that in 4 years, the radiologists will be out of job. Computers will do all the radiology analysis, etc. Of course, that was way too soon to say that. Even today, that hasn't happened. But computer or AI-based tools are a big help in radiology. Now, you give a MRI image, you can quickly the AI tool can draw attention of the doctors to the right region that it has been trained to say. And now, in spite of that, the doctor should look at the entire MRI scan again to ensure the AI has not missed something. But I think in the 99% or 90% of the cases, what the AI says will be mostly correct. Correct, I mean, that region, I mean, if it says there is not much to be worried about, that will be correct. And if it says this region is where you should look at, that will also be correct. Okay, because but you should not have 100% trust in it. So yes, it in terms of the risk or the criticality, medical diagnosis is the area where you have to be most careful about. But on the other hand, the utility and filling the gap that exists in the society, that's an area where you should employ it first, right? Because there's so much gap there.
It is a fact. At least it is a great help. At least some initial music there.
So this has to be in AI. You have to say that AI is a big helper for the human expert. Okay, as somebody said, a doctor with AI will be better than a doctor without AI. You are not even thinking only AI. That is not an option. Okay, a doctor with AI versus doctor who does not use AI. You're saying the doctor with AI will be more effective in multiple ways. Maybe you can, for the same time, they can handle 10x more patients. Maybe they won't miss things. The AI-based tools don't get tired. They don't miss things. They don't make mistakes, right? Because a computer program, it doesn't make mistakes. Whereas if you are looking at these MRI images day in and day out, maybe after 10 hours or 5 hours that you're looking at it, you will miss something because of your human weakness. That doesn't happen to an AI system. So the potential is very high. At the same time, the caution also has to be very high.
Sir, I've got a second.
Go ahead.
I am a designer of a very complex mechanical system. It uses oil hydraulics, electrical hydraulics, pneumatics, all kinds of things, several valves, several transmitters, several transducers, everything. Now, as usual, things go wrong. Okay, it doesn't work. Something has to move, it doesn't move. And then usually I am under pressure. Why it has not moved? What has happened? You tell me what is the troubleshooting. So you have to do troubleshooting. For a long time, I have been thinking, if there's a computer program which will tell me what is wrong, I will go and fix it first of all. But at the time when I retired from office, computers had not come. So that was the problem. Now, I found a new thing. See, as you say, I have to give. If this is not working, if this pressure is not okay, this temperature is not okay, maybe this is the one. We can put a conditional loop that you can do.
Yeah.
But here there is a human failure that is happening. Why?
Yes.
That see, people want to hide. You are saying bias. There is a bias. I'm not able to get all the data that is required for the thing. So I have to go and be in the field and do intuitively. Intuitively, I have to do. So can you put intuition into the computer?
That is the hardest part. That is there is a big debate in AI world. Is this, if you keep going like this, obviously the today's chatbots, LLMs they seem to do magic with language at least, and so good that we all think there is some super intelligent person or super intelligent entity behind it, because we are all, as human beings, we are used to express that knowledge and wisdom, or no, wisdom is different, knowledge and expertise being expressed in language. So now here is a system that can produce very good language. Now you think there is an intelligence entity behind it. okay, which is not true. Okay, so this whole question is, by using this method, can we, is there something called consciousness? Okay, intuition, etc., is a uh, very human property, and there is a notion called consciousness. Of course, scientists also have definition of consciousness. Now, is there a way to will this computer, this AI system, if you train more and more, you do this, you do that, will it become conscious? This is a critical question, and nobody knows how to even answer that question. There are people who claim that ChatGPT like systems are already conscious, or or they say that some people say consciousness is a totally different thing. No computer-based system can ever be. So similarly, this intuition is something that, by definition, it's coming from experience, and you cannot say why you felt it. Okay,
Yes,
and
right.
whatever these AI systems are doing, it is a deterministic program. It has a certain inputs represented using binary this and that, and it is using some statistics, some algorithm, something, and transform this to the output. So it cannot guess, it cannot read between things. You should also hope it doesn't read between things, right? Because you trust the intuition of a doctor when you come in, and just by looking at the way you walk, the doctor says things, something may be wrong, and that intuition came about from, because I don't know, 25 years the doctor has seen such patient. So that intuition you will trust. Somebody else sitting, some divine guy or somebody sitting on the screen says you have this, you obviously won't trust that person. So you don't want the computers to guess things in a way which is not supported by the mathematical model behind it. Okay, you can only trust mathematical models. Beyond that, machines cannot be trusted.
Thank you, sir. Thank you.
Okay, okay.
Sir, one more question on methodology I want to ask, sir. In vision transformers, how reliable is attention as a measure of interpretability? Like the lecture was on interpretability.
Yeah. So in language, in general,
Yes.
attention is considered interpretability. Which words contribute to something else being said, etc. Similarly, in vision also, the transformers look at the image is divided into small patches and then
Yes.
converted
Right.
into this transformer kind of model. So when you're generating new image, for instance, which part of the input image it depends on is like interpreting it, like what I showed, some of the things. Yes.
So can attention weight be trusted as a true indicator, sir, for the feature
No.
importance?
It is feature importance. It can be treated as true is a very hard thing to say, because in the
Got it.
end it is. Like even the examples I showed, GradCam, which says when you say cat, it says this is the region I think cat is there basically. That is that true indicator? I don't know. Some of these, unless you check all kinds of,
All this.
all billion images, you cannot say. But it seems to be doing the right thing. So your trust in that system improves when it says that I'm saying there is a cat because of this region. I'm saying dog because of this region. If it said I'm saying it's a cat because of something else, then you don't know. It's obviously not learning anything about cats.
Right. Okay. Got it.
Okay.
Right. Thank you, sir.
So,
Sir,
Mr. Narayanan, thank you very much.
Thank you all for
lecture and the interesting discussion actually that took place after that. Of course,
Thank
there are
you.
many more things.
Sure.
So every actually good things actually comes to an end.
Yeah.
So today also actually will bring it to a sort of end. So now actually I will request Professor Renu Sharma to present a vote of thanks. Professor Renu Sharma, please.
thank you, sir. Good evening, esteemed member present over here. On behalf of Indian National Academy of Engineering, Bhubaneswar chapter, and our esteemed partners, Shiksha Anusandhan deemed to be University, CSR, IMMT Bhubaneswar, IIT Bhubaneswar, NISER Bhubaneswar, ICT IOC Bhubaneswar campus, and IEEE Bhubaneswar section, it is my proud privilege to propose the vote of thanks on the occasion of 71st distinguished lecture of this series, held today in a virtual mode. First and foremost, we express our deep gratitude to Professor P.J. Narayanan, sir, Director of IIIT Hyderabad, for delivering an lucid and exceptional thought-provoking lecture on interpretability in computer vision. Sir, the presentation what you have given not only deepen our understanding of this rapid advanced domain, but also inspired new perspectives for researchers, scholars, and the professional, those who are attending this session today. We are truly honored by your presence and grateful for the time and expertise you graciously shared with us. I extend my heartfelt thanks to all the dignitaries, faculty members, researchers, students, professionals who joined today and made this event a meaningful with their active participation and engagement. Finally, I would like to thank our all the team members and the volunteers who work behind for their coordination and special appreciation once again to the speaker of the event. Thank you. Jai Hind.
Thank you. Thank you. I enjoyed it very much. I hope to see you all in person sometime. Online makes things very easy, but it's somewhat unsatisfying.
No, Professor Narayan, we have to come sometime.
Sure. I'll come.
We make
Yeah.
arrangement.
Yes.
Now,
Okay.
one thing that I would like to take your permission. This thing is recorded. Do you have any problem if we actually share with others?
No problem. Yeah. go
Okay,
ahead.
thank you so much. So that
Okay.
is a great thing. Now, of course, I would like to ask one or two personal questions to you.
Okay.
So in CMU, actually, we are with Raj Reddy group or Pradeep Khosla group?
No, Raj Reddy group, Pradeep Khosla group more. I mean, Raj Reddy group, Raj Reddy was heading the robotics institute. I was the computer. I was the computer vision group. The computer vision group of robotic institute under this one, Professor Takeo Kanade, who was the yeah. So I was they call research faculty member there. In CMU has a lot of faculty members who are not regular professors who just do research there. And of course, you have to bring your own money. You can't. It's not a permanent position in that sense. But
it is a great institute.
Yeah, so I was there. But in CMU, you can co-guide students. You can do all kinds of things as research faculty. You are almost like a postdoc only, but you can do more things there. Yes.
No, in fact, actually, in the initial days, RGUKT days, so I have visited several times actually your institute.
Yeah.
And in fact, we used to stay in your guest house.
Oh wow, nice. Rajkumar days, right? Professor Rajkumar.
Raj Reddy actually was there.
Yeah.
He was your also chancellor, that RGUKT chancellor.
Yes. So he stepped down from our chancellorship, our chairmanship 2 years ago. But he's 89. He'll be 89 in another 2 months.
No. He is actually a highly respected person.
So he's coming.
This university.
Yeah, he's coming again in February. He'll be here for a month and a half. He usually stays in our campus in the guest house.
No. Every year actually he comes.
Yeah.
So now, who has really succeeded you in?
And Sandeep Sharma he's in IIT Kanpur. He's come.
Okay.
Yeah.
So, Professor Narayan, sometimes when I come to Hyderabad, I will definitely meet you.
Please let us know. We can come here. Stay in our guest house.
My daughter stays in Hyderabad.
So
I have
okay.
no reason that actually why I have to come.
So let us know when next time you are here. We'll meet.
Oh, sure. Okay.
Thank you all.
Thank you so much.
Thank you. Bye.
Thank you, sir.